Okay, next exercise 8. It has two parts. Part A, verify that for all integers n greater than or equal to 1, this identity is true. 2 times 6 times 10 times 14 etc. up to 4n minus 2 is equal to 2n factorial divided by n factorial. And then there is part B. Use part A to obtain the inequality. Two to the power n divided by times n factorial square is less than or equal to 2n factorial. For all n greater than or equal to 1. So let's see the solution. First we solve part A. The given identity is true for n equal to 1. When n, given identity means this one. When n is 1, the left hand side has exactly one factor. By the way, how many factors are there in the left hand side? You see, 2 can be written as 2 times, is it 2 times 2 minus 2? Yes. Then 2 times 3 minus 2, because no, I think I am getting it incorrectly. For n minus 2, if I put n equal to 1, I get, oh, why am I writing 2? Sorry about this. 4 times 1, 4 times 2, 4 minus 2 is 2, 8 minus 2 is 6, 12 minus 2 is 10, 16 minus 2 is 14, etc. Like that we are going up to 4n minus 1. So looking at this pattern, you can clearly see that this product has n terms. Now when n is equal to 1, there is only one term, and from this expression you can see that that term is 2. So when n is 1, the left hand side is 2, and when n is 1, the right hand side is also clearly seen to be 2. The denominator will be 1 factorial and the numerator will be 2 factorial. So we have a basis for our induction. Assume that the identity is true for some n greater than or equal to 1 for some positive integer, that is this. Then we are going to consider the case where in place of n we have n plus 1, that is one more factor. What will the next factor be? To see what that is, you replace n by n plus 1, that gives us 4n plus 4 minus 2, that means 4n plus 2. So we can use this part, that our induction hypothesis, to write this product as 2n factorial divided by n factorial times, now we have 4n plus 2. Okay, now 2n factorial stays as such. From this term we take a 2 common out. We are then left with 2n plus 1. In the denominator we have n factorial. Now what we do, we multiply and divide by 2n plus 2. Oh sorry, it will be 2n plus 2 inside brackets. Now this becomes equal to, you see we can cancel this 2 and these 2's out. Doing so, we are left with 2n factorial times 2n plus 1 times 2n plus 2. In the denominator, we are left with n factorial times n plus 1. So this is 2n plus 2 factorial divided by n plus 1 factorial, or 2 times n plus 1 factorial divided by n plus 1 factorial. So you see that this is just that same identity, where in place of n we have n plus 1. On the right hand side also it's that same, it has that same form. So by the first principle of finite induction, the given identity is true for all integers n greater than or equal to 1. Now the next part asks us to use this identity and obtain this inequality. So this is part B. For that we claim something, another inequality, and we prove that claim using induction, which will then help us get this inequality. We claim that for all integers n greater than or equal to 1, Okay, let me just think of it for a moment. We need, if we take this common out, then n factorial has to be greater than or equal. Okay, yes, 1 times 3 times 5 times 7 up to 2n minus 1. We are claiming that this is greater than or equal to n factorial. This is our claim. This inequality is true for n equal to 1. When n is equal to 1, the left hand side is 1, the right hand side is also 1. So in this case we actually have equality. Now we make the induction hypothesis. For some integer n greater than or equal to 1, then what happens if we put one extra factor here? The next, because we are considering odd natural numbers, the next odd natural number is 2n plus 1, or you can obtain that from here itself by replacing n by n plus 1. Okay, so this part is greater than or equal to n square. That means, n factorial. So this will be greater than or equal to n factorial times 2n plus 1. Now we can replace 2n plus 1 by n plus 1, and we have the inequality intact. The inequality does not get reversed. The thing is that 2n plus 1 is clearly greater than n plus 1. Why is that so? You see that 2n plus 1 is greater than or equal to n plus 1. In fact, strictly greater than n plus 1, because if you rearrange the terms, you can see that this inequality is equivalent to the other inequality, which is n is greater than 0, which is true. So that's why we can write like this, and this last term is nothing but n plus 1 factorial. So by the first principle of induction, our claim has been established. Let me keep the exercise and wrap this part off instead. Now, by part A, for any integer n greater than or equal to 1, we have what? let's start with this, with the left hand side of this inequality that we have to show. This can be written as exactly what should I write? Should I directly use this claim here itself? Let's use that claim itself. You see, n factorial is less than or equal to this. So that means this can be written as less than or equal to n factorial times 2 to the power n times 1, 3, 5, 7, etc. up to 2n minus 1. So what we have done here, we have kept one n factorial intact, and along with that 2 to the power n. The other n factorial has been replaced by the possibly bigger product, by that inequality which we have already proved. Now this is equal to n factorial. Now you see, in this product there are exactly n terms. How can we say so? It's because you can view 1 as 2 times 1 minus 1, 3 as 2 times 2 minus 1, 5 as 2 times 3 minus 1, and so on, 7 as 2 times 4 minus 1. So whatever number you have here, that denotes the number of factors we have got so far. So by the time you reach this, you will have n factors, because you see, if you consider only this one, you have 1 here and there is only one factor. If you get to 3, you have 2 here, there are 2 factors, 1 and 3. If you get to 5, we have 3 here, and here also there are 3 factors. So when you get to this, there will be n factors. Okay, so what we plan to do now is that we want to distribute this 2 to the power n among all the factors. Each one gets a 2, each one is multiplied by a 2. If you do so, you will have 2 times 6 times 10 times 14, etc. up to 4n minus 2, and this is where we can use part A. Using that, we get n factorial. This product is equal to 2n factorial divided by n factorial. And that becomes what? N factorial, they cancel out, and we are left with 2n factorial. So that means this is less than or equal to 2n factorial. That is the second inequality. So here the solution ends. The next exercise 9. Establish the Bernoulli inequality. If 1 plus a is positive, then 1 plus a whole to the power n is greater than or equal to 1 plus NA for all integers n greater than or equal to 1. Here A is some real number which when you add with 1 the sum is greater than 0, the sum is positive. Then we have to prove this. It's very easy actually. The inequality is true when n is equal to 1. In fact, in this case it just becomes an equality. The left hand side becomes 1 plus a, the right hand side also becomes 1 plus a. So here it's true. Now the induction hypothesis. Assume that this is true for some integer n that is positive. Then 1 plus a whole to the power n plus 1 can be written as 1 plus a times 1 plus a whole to the power n, and this will be greater than or equal to 1 plus a times 1 plus n a. Where we have used the induction hypothesis, note that both sides of this inequality have been multiplied by 1 plus a, and we still have the inequality has not changed in direction, it has not got reversed. That is because 1 plus a is given to be a positive real number. So that's why we can write like this. Now if we multiply the terms out, we get 1 plus n plus 1a plus n a square. Whatever a is, whatever real number a is, a may be negative also, keep that in mind. A may be negative but so small that 1 plus a is ultimately greater than 0. But a square is non-negative. A square can be, the least value of a square is 0. And the greatest value, of course, it can be as large as we want, because we only want 1 plus a to be greater than 0. A can be extremely large. The thing is that n a square itself is a non-negative real number which has been added to this, added with 1 plus n plus 1 times a. So if we write simply 1 plus n plus 1 times a, then we are possibly writing less. I say possibly because a may be 0. In that case, this will be equal to this. Otherwise, this is positive. So then writing this, we are actually writing less. So in any case, this is greater than or equal to 1 plus n plus 1 times a, which you can see is just the given inequality where in place of n you have n plus 1. So by the first principle of finite induction, for all integers n greater than or equal to 1. So this completes the solution to exercise 9. Exercise 10. For all n greater than or equal to 1, prove the following by mathematical induction. So there are two parts. One by 1 square plus 1 by 2 square plus 1 divided by 3 square, etc., plus 1 divided by n square is less than or equal to 2 minus 1 by n. That is one thing. And part B, 1 over 2 plus 2 over 2 square plus 3 over 2 cube, like that, plus n over 2 to the power n is equal to 2 minus n plus 2 divided by 2 to the power n. Should not be very complicated. The given inequality is true when n is equal to 1. When n is 1, the left hand side has only one term in the sum, which is this first term, which is 1, and when n is 1, the right hand side is also equal to 1. So in this case we actually have equality. Assume that for some positive integer n, then use the induction hypothesis to replace the first part of the sum except the last term by this and bringing in an inequality, 2 minus 1 by n plus 1 by n plus 1 whole square. Okay, now so we want this to be less than or equal to 2 minus 1 over n plus 1. For that to happen, that means I need minus 1 over n plus 1 here. Okay. Now n plus 1 n into n plus 1 and okay, now n plus 1 is greater than n. That is obvious, because and anyway n is, in fact this is true for any integer n, not just positive integers n. So this is true, which implies multiply on both sides by n plus 1. We can do that without reversing the inequality, because n plus 1 is positive, which implies n plus 1 whole square is greater than n times n plus 1. Thus 1 over n plus 1 whole square is less than 1 over this, and this term is equal to, if you look carefully, this is 1 over n minus 1 over n plus 1. If you take LCM and then do all the calculations, you will end up with 1 over n times n plus 1. This implies less than or equal to 2 minus 1 by n plus 1 over this. Now this is strictly less than this, so we can replace it by that. So this will be strictly less than 2 minus 1 over n, and this thing is less than or equal to 1 over n minus 1 over n plus 1, and this becomes 2 minus 1 over n plus 1. So you can see that this inequality, when in place of n we have n plus 1, that is we have one extra term in this sum, is less than or equal to 2 minus 1 over n plus 1. So that just completes the induction. So by the first principle of finite induction, the given inequality is true. Then part B, same, when n is 1, the left hand side is 1 over 2. When n is 1 here, the right hand side is 2 minus 3 divided by 2, that is 4 minus 3 whole divided by 2, or 1 divided by 2. When n is equal to 1, both sides of the given identity are equal to 1 over 2. So that means it's true when n is equal to 1. Assume that the identity is true for some non-negative integer, for some positive integer n, then this is equal to 2 minus n plus 2 over 2 to the power n plus this becomes equal to 2, we will keep 2 as it is, because in the final form also 2 is just there alone. What happens to this part? Minus, if we take 2 to the power n plus 1 LCM, then we have to multiply this by 2, so we will get 2n plus 4, and since we have taken minus outside, so here we will have minus n minus 1, so this becomes equal to 2n minus n is n, and 4 minus 1 is 3. So this can be written as 2 minus n plus 1 plus 2 divided by 2 to the power n plus 1. So you can now see that this is in this form, where in place of n we have n plus 1. So by the first principle of finite induction, the given identity is true for all positive integers n, and this completes this exercise. Show that the expression 2n factorial divided by 2 to the power n times n factorial is an integer for all non-negative integers n. There are two ways of solving this problem. One, of course, if you can directly use induction on n. The other comes from the solution to exercise 8b, where we actually encountered this ratio. So since induction proof is, you already know how to do it, let's just see the other solution. Let's just write like this: the expression 2 times 0 factorial divided by 2 to the power 0 times 0 factorial is equal to the integer. What integer will it be equal to? In the numerator we have 0 factorial, that means 1. In the denominator also this is 1, this is 1. So that means the integer is 1. For n greater than or equal to 1, it follows from the solution to part B of exercise 8 that this expression is an integer. Let's see. Then exercise 12, only a few are left, let's just finish. Consider the function defined by t of n is defined to be equal to 3n plus 1 divided by 2 for n odd. When n is an odd natural number, then 3n plus 1 divided by 2, and its value is n divided by 2 when n is even. There is a conjecture involving this function which I think still is unsolved in this form. The conjecture is that if one keeps on applying t to an integer n, to a positive integer n, then one will eventually end up with the number 1, and then after that the values will be trapped among the values 1 and 2, because you see, if you get keep on applying t means you apply t on n where n is some positive integer, then on that you apply t, then on that you apply t. If you keep on doing that, the conjecture is that you will end up with 1. Now when you have 1, then what is t of 1? Because 1 is odd, we have to use this part of the formula. So we will get 3 plus 1, 4 divided by 2, so this is 2. On that, if you again apply t, because 2 is even, this part of the formula will be used, giving you 1. So it will then alternate between 1 and 2. Whether this itself is Collat's conjecture or not, I don't really remember. We will see. The 3n plus 1 conjecture is the claim that starting from any integer n greater than 1, the sequence of iterates Tn, T of Tn, T of Tn, etc. eventually reaches the integer 1. And subsequently runs through the values one and 2. This has been verified for all n less than or equal to 10 to the power 16. 10 to the power 16 is a very large number. 1 followed by 16 zeros. Confirm the conjecture in the cases n equal to 21 and n equal to 23. T of 21, since 21 is odd, we have to use this part. Applying the formula, you get 32. So 32 is even, so it will be halved 16, which is again even. So this will be 8. T of 8 is 4. T of 4 is 2 and T of 2 is 1. And then T of 1 is 2. Again T of 2 is 1, and it will continue like this. Also, and the other value is 23. T of 23, I have the values here with me, is 35. So for some time it increases, for a number of steps. T of 35 turns out to be 53. Then T of 53 is equal to 80. Then T of 80 is, of course, it will be halved since it's even. And again T of 40 is 20. T of 20 is 10. This will continue as long as we have even integers. T of 10 is 5. Then again it increases. T of 5 is 3 times 5, that is 15, plus 1, 16, divided by 2, 8. But the moment we get 8 is a power of 2, so the halving process will continue till we get 1. So this is 4, and the rest is, of course, it will just like this. It's still let's just write for the sake of completeness. One, when t of 1 is 2, t of 2 is 1, and it keeps on alternating between 1 and 2 like this. There are two more problems, two more exercises that that use the second principle of finite induction, but we will do that in the next video. Okay, I'm not feeling quite well today, and it's extremely late at night also because of the technical difficulty we were going through, which jeopardized the schedule. I'm trying to catch up in this week at least. So tomorrow there will be a graph theory video, and after that, from the next week, the usual things will flow in the usual way. I know I was supposed to touch upon that chapter 2 also, where we will now solve the exercise problems. And one more thing, that example that I got wrong in the previous video, that example 2.1, there the expression was not this, but in place of 1 we have 2. This is always an integer irrespective of the value of a, which a itself is a positive integer. Whatever a is, this is always going to be an integer. We will see these things in the next video. Okay. So with this I sign off. This is me, Lucifer, from a mathematical room. Have a nice night.